Welcome to the Week 3 lesson. Along with this lesson, you will find an Excel file called Descriptive and Inferential Statistics Example. Please use this to refresh yourself with some of the functionality of Excel. Note that there is a tab for you to work in and a second tab that has the calculations completed should you get stuck. As always, please post any questions you might have in the class coffee shop. In this lesson, we will try and connect the probability theory we have talked about with how we actually apply it in sampling to draw conclusions about our population. Let's take a moment to refresh the theories that control sampling distributions. First, the law of large numbers allows us to assume that by collecting enough samples, our sample mean will provide a good estimate of the population mean. And second, the central limit theorem allows us to assume that a large enough sample provides us a sampling distribution that will be approximately normal no matter what the population distribution looks like. Together, these theorems mean that even if we do not know the shape of our population distribution we are sampling from, we can draw inference about that population if we take enough samples. So, if we need enough samples to assume our sampling distribution is normal, how many samples is enough? Well, first, if you already know your population distribution is normal, which we don't often know, then any sample size will also be normal. However, if we don't know the population distribution, or if we know it isn't normal, then we need to collect enough samples to assume the sample distribution is normal. Most statistics books will say when n is greater than 30, we can invoke these ideas. However, things are not that simple in practice. The thing to remember is that as a variable's population distribution becomes less normally distributed, more samples are required. This means we need to use our judgment and knowledge as managers to determine how variable we think a population is, to determine how many samples are needed to invoke these ideas. Once we have a sample from a population, we will want to draw some conclusions about that population. The first thing we do with our sample is to generate a point estimate, which is a single value that estimates a population parameter from a set of samples. An example of this would be estimating the population mean from our sample mean. As we have discussed, these estimates are subject to error. The sample mean, shown here by the X bar, approximates the population mean, commonly denoted with a mu symbol, but is rarely a perfect match for it. A key to understanding how we achieve precision in sampling is grasping how the variability in the sample mean is scaled by the sample size. This variability is called the standard error of the mean, where the standard deviation of the sample variable, little s, is scaled by the amount of effort, or sample size, that went into it, and provides an estimate of the population standard deviation. Within all sampling designs, we want to be able to determine the accuracy and precision of our process. With this in mind, let us look at assessing the accuracy and precision of an archer shooting at a bullseye. In the case of archery, the calculation of accuracy and precision is fairly straightforward. The distance of the arrows from the bullseye indicates the accuracy, while the spread of the arrows reflects the precision. What if I had to tell you to shoot without having a bullseye? This is the case in sampling, since the bullseye is unknown. This makes assessing the accuracy and precision of a statistical estimate not as simple. The spread still reflects the precision of the process, but the holes only provide an estimate of the bullseye, or accuracy. A confidence interval allows us to estimate the true value of the bullseye without knowing anything about the population distribution. After looking at how probability theory characterizes our sampling distribution, we can begin assessing our confidence in a sample. This requires us to use the concepts of inferential statistics to determine how well our sample approximates the population. We do this by developing confidence intervals that describe the range of possible values an unknown population parameter could have. We interpret these intervals as meaning that for a 95% confidence interval, 19 out of 20 samples, or 95 out of 100 samples, from the same population will produce confidence intervals that contain the population parameter. Now let us break down the pieces that go into a confidence interval of a population parameter. The first component is the point estimate of a sample statistic from a probability sample. We will focus on doing this with a sample mean, although other sample statistics may be more desirable, such as a median or variance. The second component is the margin of error. This is the piece of the confidence interval that accounts for errors in the point estimate and the fact that our sample statistic will not exactly match the population parameter. Our margin of error is what gives us the range of possible values the population parameter could have. Together, this tells us the confidence interval is equal to the sample statistic plus and minus the margin of error. The margin of error requires a little more dissecting as it is composed of two pieces, the confidence level statistic and the standard error, where we multiply these together to equal the margin of error. Remember that the standard error is an estimate of the population standard deviation that equals the sample standard deviation divided by the square root of our sample size. The other half of the margin of error tells us that every confidence interval is produced with a desired level of confidence. Generally, we are interested in having 95% confidence, although in other applications you might desire a different level of confidence. In medical research, for example, you might desire a 99% confidence level. The confidence level is a probability indicating how much certainty we should attribute to our confidence interval. All other things held constant, a higher confidence level will produce a wider confidence interval. Put another way, a wider confidence interval will give us more confidence that the true test statistic is within those bounds. Generally, we do not know the population standard deviation and mean, which we could use to calculate a confidence interval. Without these, our confidence level comes from the t-distribution, which is derived from the t-statistic. We can calculate this in Excel, as you will see in a moment, or can simply use a t-table to look up the statistic. The distribution produced by the formula is a symmetrical curve with a mean of 0 that has its width controlled by our degrees of freedom, which equals little n minus 1. The control degrees of freedom has over the t-distribution's width can be seen in this graph, where the z-distribution, with infinite degrees of freedom, is a perfectly normal distribution, where 95% of the possible values fall within 2 standard deviations of the mean. The t-distribution's 95% values vary according to the degrees of freedom, with it being 2 standard deviations of the mean when the degrees of freedom are infinite, and more than 2 standard deviations from the mean when the degrees of freedom are less than infinite. At smaller sample sizes, the tails of the distribution lengthen. If we know the confidence level we want to work at and have our degrees of freedom, we can determine our t-value from a t-table, or we could calculate a more exact value using Excel. In Excel, to do this, we want to calculate the two-tailed t-value using the equation t.inv.2t, and then in parentheses we provide the type 1 error probability, which we'll discuss more below, and our degrees of freedom, separated by a comma. If, for example, we needed to find the t-statistic for a sample of n equals 10 at a 95% confidence level, our degrees of freedom would equal little n minus 1, or 9, and the probability needed for this function is the type 1 error probability, which is the probability of the value falling outside of our range of confidence. We calculate this by subtracting our desired confidence probability from 1. Because we are interested in a 95% confidence level, here it would equal 0.05. To get our test statistic in Excel, we would put 0.05 and 9 inside the parentheses of the function separated by a comma, giving us a t-value of 2.262. This gives us a value 13% larger than the value of 2 that the z-distribution would give for a 95% confidence interval. This added width in the distribution is to account for the fact that we do not know the population standard deviation. A fun piece of statistical history to add to this story, the original work developing the t-test and t-distribution were done by William Seeley Gossett in the early 20th century. Not only was Gossett an amazing statistician, but he was the chief brewer at the Guinness Brewing Company in London. Due to a Guinness policy that excluded employees from participating in science, Gossett published his work under a pseudonym name Student. This is why the t-distribution is sometimes called the student's t-distribution. His work also led to significant breakthroughs in the fields of agriculture and genetics. Okay, we have now figured out how to get all of the pieces that go into describing the interval of values we would expect a population parameter to fall within. Let's try an example. Say we collect 9 variable radius forest inventory plots that reveal a mean basal area of 130 square feet per acre and a sample standard deviation of 15 square feet per acre. With 95% confidence, what would be the estimate of the population mean? Because we already have the point estimate of the population mean, which is 130 square feet per acre from our sample, our first step is to determine our margin of error, which you'll remember is calculated by multiplying the t-statistic by the standard error. We use Excel to calculate the t-statistic, as we did earlier, and find that it is equal to 2.3060. The standard error is equal to the sample standard deviation, 15 square feet per acre, divided by the square root of the sample size. Our sample size here was 9. Our standard error therefore equals 5 square feet per acre. Multiplying these together gives us a margin of error equal to 11.53 square feet per acre. With the margin of error, we can make a statement about the possible values that the population parameter could take. Remember, the confidence interval is calculated from the sample statistic and the margin of error. Our sample statistic of interest in this example is the mean, which we found to be 130 square feet per acre. The margin of error, calculated on the last slide, gave us 11.53 square feet per acre. Adding the margin of error to the sample statistic gives us the upper confidence limit, while subtracting the margin of error from the sample statistic provides us with the lower confidence limit. With these data, we can say with 95% confidence that the mean from another random sample should fall between 118.47 and 141.53 square feet per acre. We may also wish to state the margin of error as a percentage of the statistic. The way we just calculated the standard error is by dividing the sample standard deviation by the square root of the sample size. If we are interested in scaling this to be a percentage of the sample statistic, which is also known as a relative standard error, we would simply take the standard error and divide it by the sample statistic, the mean in this case. Although it may seem more obvious to use a number to present the standard error, scaling to the sample mean can be quite beneficial when communicating results across studies and organisms. For instance, the margin of error for the basal area of a lodgepole pine sample would be a much smaller number than the margin of error for a redwood tree sample, since redwoods are so much larger, even if the percentages were the same. We might then conclude, incorrectly, that the sampling effort for redwoods had a higher error. Using percentages, we can accurately compare the margin of error from each sampling effort. If we were to rework the basal area example as a percentage, we would start with our sample mean of 130 square feet per acre and standard error calculated previously of 5 square feet per acre. We scale this standard error by the sample mean and recalculate the margin of error by multiplying the t-statistic by our standard error divided by the sample mean. Our new margin of error is 8.87%. We would then report our confidence interval as 130 square feet per acre plus or minus 8.87%. Now let's look at what we mean by efficiency in sampling and the things that impact the efficiency of our sampling design. Efficiency is a measure of the optimality of an estimator, experimental design, or of a hypothesis testing procedure. A more efficient estimator, experiment, or test needs fewer observations to achieve a given precision. When we look at how efficiently a statistic provides an estimate of a population parameter, two things interact to control this process: the population variability and the sample size. A general rule of sampling is that as a population's variability, or the range of possible values an observation can have, increases, the number of samples necessary to achieve a desired precision increases. Meaning that the larger our population standard deviation is, the more samples we need to be more precise. This idea has a strong connection with the law of large numbers, which says that with enough samples, the sample statistic will approach the population parameter. When the standard deviation is high, however, the amount of samples required to be enough increases. We can see the effect that the population variability has on our sampling efficiency by drawing multiple samples of n equals 10 from both a normal distribution and a bimodal distribution. The variability about the true mean narrows down sooner for the population with a narrower range of possible values, which is the normal distribution. Our second controlling feature was the sample size. If we continue to sample from the two distributions, our sample statistic will stabilize around the population parameter. For the normal distribution, this happens by around a sample size of 20, but because of the extra variability in the bimodal population, it takes a sample size of about 40 to stabilize. When we bring these two effects together, we can see how population variability interacts with sample size to influence our sampling precision and ultimately our sampling efficiency. Under both of these scenarios, we can change our sampling design to improve our sample efficiency. We will look at this more in the coming weeks. Although we may be enticed to think that more is better, we also don't want to waste time and resources collecting more samples than we need. At some optimal sample size, the precision and error in estimating a population parameter will asymptote, or level off, and we will see a point of diminishing returns, where each extra sample collected doesn't actually increase our precision or decrease our error very much at all. In statistical theory, this leveling off is a mathematical result of probability theory. In the real world, it can be caused by a number of constraints on our sampling system. When working in the real world, we have many constraints on our sampling efficiency to contend with. These most commonly include the time required to complete the work, money to perform the work, and the desire to understand the population. Each of these must be considered when defining the efficiency of sampling within the real world, and when designing your sampling protocol. It is fairly intuitive how time and money could influence our ability to sample as much as statistical theory says we should. However, the third reason is not as transparent. Sometimes we need information about something that is just not important in the grand scheme, so we decide a minimal confidence is needed. If you have valid reasons, there is absolutely nothing wrong with doing this. Stopping a sample because of any of these constraints is perfectly reasonable and does not make anything biased. For instance, I was part of a sampling team a few years ago, sampling the understory vegetation in a forest following a major fire. In the fourth year, we had to cancel the last few days of sampling because high winds were blowing the burned trees down all around us. We had the time, money, and desire to complete the work, but unsafe conditions were our real-world constraint.